So today we're going to be solving Cambridge International AS and A Levels Chemistry Paper 2 AS level structured questions, May June 2025 and Paper 21. It's a 1 hour 15 minutes paper, and in the first part we're going to be solving the first two questions, and in the second part we're going to be solving the remaining two. So let's get going. Solid sodium, okay, conducts electricity. We know because solid sodium, it's a metal, and we know metals are going to conduct electricity by the movement of metals conduct electricity because of the electrons present in the metal. Okay, sodium oxide conducts electricity when molten but not when solid. Why? Because we know sodium oxide, it's a ionic compound, and we know that ionic compounds, because sodium is a positively charged cation and oxide is a negatively charged anion, so sodium oxide is going to be an ionic compound, and we know that in ionic compounds, when they're solid, the ions are stationary, but when they're molten or they are in aqueous solution, the ions are mobile. So it's only going to conduct when it's molten or aqueous. We know it. Name the types of bonding present in sodium and sodium oxide. This is an IGCSE level question, that the bonding in sodium, it's going to be definitely metallic bonding because sodium is a metal, and the bonding in sodium oxide, it's going to be ionic bonding. So that was easy. Explain how sodium conducts electricity. We know that it's going to conduct electricity. They're very important in that in AS level you can't mess up by just writing electrons. Electrons is not a proper word. This is not going to give you marks. The thing that you need to write is that proper delocalized electrons move through the metallic lattice of sodium to conduct charge. To conduct, you can say charge or you can say electricity. So in O levels, when or IGCSE, when this question used to come, that why a metal would conduct electricity, you'd only be given a single line. But in AS level, the examiner deliberately gives you two lines. You know why he deliberately gives you two lines? Because he wants a proper explanation of every word, that they're delocalized electrons, they move through the metallic lattice. Open up the marking schemes, you're going to figure this out yourself. Explain why sodium oxide conducts electricity when molten. So simply, in molten Na2O, there are free mobile ions that can move through the liquid. Okay, words are important. That can move through the liquid to conduct electricity. Done. Next, you can also tell that there are positively charged sodium ions and there are negatively charged oxide ions that can move, but the word ions is going to do the job. The word ions can do the job, but if you write this and this, they're going to be added benefits. Okay, because when you get a distinction, it's like they check the extra details as well. So it's good that you add details in your answers. They're going to make it look better, though you're going to get the marks by writing ions. Okay, separate samples of sodium and sodium oxide are added when excess of cold water. Write an equation for the reaction of sodium with cold water. This is again O levels based stuff. You add sodium, do we have to add state symbols? No, we don't. You add sodium to water, what do you form? You form sodium hydroxide and hydrogen gas, and you have to balance this equation because there are a total of 2 hydrogens on this side and a 3 on this side. So you added 2 over here. When you added 2 over here, now the oxygens also become 2, so you have to add a 2 over here as well. So you added 2 over here, and now sodiums are also 2, so you added 2 over here as well. Now this is a balanced equation. Write an equation of the reaction of sodium oxide with cold water. Okay, so when you have sodium oxide and you add cold water to it, now you're not going to form hydrogen gas. Now you're only going to form sodium hydroxide. Okay, remember this. When you add a metal, a group 1 or a group 2 metal, not all group 2 metals, not magnesium specifically, because magnesium reaction with cold water is very slow, but still it might take some days, but still it's going to react. So when you add a metal to water, you form hydroxide and hydrogen gas. But when you add a metal oxide to water, what do you form? When you add a metal oxide to water, you form only hydroxide. So over here, you're not going to form hydrogen gas, you're going to form sodium hydroxide, and you put A2 here to balance out the hydrogens. And now you added 2 over here. Oh no, it was Na2. Oh, sorry, it was Na2. Right, are we balanced? Balancing takes a time. Yeah, it's balanced. Good. Okay, complete the table. Do not refer to the temperature changes when considering observation. So if anyone writes temperature increases, that's not going to be marked. Okay, one similarity in the observation on addition to cold water. Okay, so we have to write one similarity when sodium is added to cold water and sodium oxide. Now you need to consider, obviously you cannot write it unless you don't imagine that you have 2 beakers, and both of the beakers, they contain H2O, okay? And now you add a piece of sodium to this beaker and a piece of sodium oxide, though it's going to be a white solid, but I'm making it with pink, to this beaker. Now what's going to happen? You yourself, I guess, are good enough in imagining when you add this piece into water and this piece into water, what's going to happen? These pieces are going to react, and when they're going to react, slowly the solid is going to disappear, okay? Because the reaction is happening. So you're going to say that a white solid disappears, forming a colorless solution. I guess that was obvious enough. And one difference, you can see the equation to figure out the difference, that in this equation you can see over here you are producing hydrogen gas, and over here there's only sodium hydroxide, because when you're producing a gas, what's going to happen? You're going to see effervescence. So for sodium, one difference in observation with cold water, you're going to see effervescence of a gas and no effervescence. Or you can also write effervescence of a gas that pops with the lighted splint, whatever, that pop test for hydrogen gas you can write as well. But effervescence will give you marks. Done. State the oxidation number of the period 3 elements bonded to chlorine in NaCl and PCl5. Explain the difference in the oxidation number. Okay, so what the examiner is trying to say is state the oxidation number of period 3 elements bonded to chlorine in NaCl and PCl5. So now you can see for yourself that in NaCl, Na is a period 3 element, right? So the first thing is that in NaCl, NaCl, Cl is a negative one and Na is a positive one. And in PCl5, you can see for yourself that since chlorine is more electronegative than phosphorus, so chlorine is going to be a negative 1, and when you have 5 chlorine, so you multiply negative 1 times 5 and you get a negative 5. A negative 5 on chlorine, and to balance out this negative 5, there's going to be a positive 5 on phosphorus. So now in this PCl5, there is a positive 5 on phosphorus and a negative 1 on chlorine. So the difference is that sodium is going to form only a positive 1 and phosphorus is going to form a positive 5. And why is that going to happen? Explain the difference in the oxidation number. Explanation is because sodium can only lose 1 electron. It's in group 1, whereas phosphorus can lose 5 electrons. It's in group 5, so it can have a positive 5. So the oxidation number, the statement is going to be Na has an oxidation number of a positive 1, whereas your phosphorus, it has an oxidation number of positive 5. And why? Because you know that sodium is in group 1, whereas phosphorus is in group 5. That means that phosphorus atom in its valence shell, it has 1, it has 1, 2, 3, 4, 5 electrons. So basically it can lose all 5 electrons. All 5 electrons can be lost by phosphorus. They can move out of phosphorus. Whereas a sodium atom, it only has 1 electron, so it can only lose 1 electron. Whereas phosphorus can donate all its 5 electrons to chlorine, but sodium cannot. I hope you get this thing. Okay, moving on to the next question, which says that table 1.2 shows the melting points of some oxide. Okay, a student suggests the following hypothesis. Okay, the higher the oxidation number of an element combined with oxygen, the higher the melting point of the oxide. The higher the oxidation number of an element. Okay, we need to figure out the oxidation numbers. Okay, sulfur over here is going to be a positive 4, hydrogen going to be a positive 1, sulfur positive 6, positive 4, positive 2, positive 3. Done. The higher it is, the higher the melting point. No, the highest oxidation number is of sulfur trioxide, and it does not has the highest. The highest melting point is of magnesium oxide, whereas the highest oxidation number is of sulfur oxide. So this hypothesis, use table 1.2 to reduce if this hypothesis true or false if there is not enough information to make a conclusion. I believe this is false because we can see that the highest oxidation number is sulfur trioxide, but the highest melting point is of magnesium oxide. So we're going to write that this is false because the highest oxidation number is of SO3, but which is plus 6. Let's tell them that we have figured it out, which is plus 6, whereas the highest melting point is of MgO, which has an oxidation state of plus 2. Okay, plus 2. So I guess that's enough. We've told ourselves. A sample of iron is analyzed using a mass spectrometer. The mass spectrum shows 3 isotopes of iron present in the sample. Define isotopes. So isotopes are atoms of the same element. You have to write this with same proton number. I learned it in O-levels IGCSE and I still remember. You should also remember. This is easy. Same proton number but different neutron number. That's all. I hope we get a 1 mark. Acha, figure 1.2 shows the mass spectrum of the sample of iron. Okay, we have a sample of iron and we're shown with the percentage abundance. We're given with the mass. Using figure 2.1 to calculate the relative atomic mass of iron to 1 decimal place, show you're working. Okay, that's simple. What's the percentage of the first? It's 59 and 54 is the mass. So 54 multiplied by 5.9 plus what's the mass of the second? It's 55. No, it's not 55. It's going to be 56 because 55 is 0 abundance. So it's going to be 56 times what's the abundance? 91.9. 91.9 plus it's going to be 57, the mass of the third one, multiplied by its abundance, which is 2.2, divided by the sum of all abundances. Since we're dealing in percentages, it's going to be 100. Where's my calculator? I'm going to plug this entire thing into my calculator and I'm going to see what do I get. So it's going to be 54 times 5.9. Okay, it's going to be upon 100 plus 56 times 91.9 plus it's going to be 57 times 2.2. And that gives me 55.9. So it's 55.9. This is not gonna work, so let me import this document. So now we were here. Okay, so it's gonna be 55.9. 55.9 is our AR that we got, and make sure that you write it to one decimal place, because if you because on the calculator I'm getting 59.04, but if I try to add 59.04, that's gonna be messed up, because the examiner stated clearly that it should be up to one decimal place. Okay, complete table 2.1 to show the number of protons and nucleons in one atom of iron. 56 protons are going to be 26. Check from the periodic table. Nucleons are going to be 56 minus 26. That's going to be 30. This paper is easy. Okay, deduce the number of pairs of electrons in the shell with the principal quantum number 3 in an Fe atom. Okay, so in the third shell we have to reduce the number of pairs, not the exact number of electrons. Okay, let's go to the periodic table and see where iron lies. Okay, this is iron. It is 26 electrons, and if you try, this is 1 2 3 4, and this is 3. So the last shell of iron is 4s2. This is the s1. In the s1, if you move from here, this is 4s1, this is 4s2. So 4s2 and 3d 1 2 3 4 5 6. 4s2 and 3d6. So 6 7 8. So there are 4 pairs, right? There should be 4 pairs, but you need to consider one more thing as well. What do you need to consider? Look, 4s2, 1 and 2, and 3d 1 2 3 4 5 6. When you're gonna make it, like, look, number of pairs of electron shell with the principal quantum number 3. There are in the last shell there are, it's 4s2 in the last shell and 3d6, but we cannot consider 4s2. Why cannot we consider? Because it is principal quantum number 3. So we are only looking for in the third shell, and if we know it's going to be 3s2, 3s2, 3p6 and 3d6, right? That's going to be the 3 quantum number, which makes a total of 6 plus 6 12 13 14 electrons. And that's a simple principle. Look, what's gonna happen is that you might consider it 7 because it's 14 electrons. Okay, I agree with you, but there's one thing I need to tell you guys which might change what you think. That, look, this is 3s2, this is 3p6, and this is 3d whatever. Okay, so there are 2 electrons here, 2 electrons here, 2 electrons here, 2 electrons here, and over here there's 6 electrons. And you know, according to Hund's principle, what happens is that electrons are not going to fill like 1 2 3 4 5 6, not at all. What they're going to do is that they're going to first they're going to occupy the empty orbitals like this. So this electron right here, it's going to move here, it's going to move here, and this electron right here is going to move here. So accordingly, if we look at the paired electrons, because these 2 electrons that were here, that you were considering a total of 7 pairs, like 1 2 3 4 5 6 7, they're not going to be 7, they're going to be 5, because electrons, they're going to occupy the unfilled orbitals as well. Why? Because when they're paired, they face spin pair repulsion, and electrons don't want to face spin pair repulsion. So what they're going to do is they're going to first fill the empty orbitals. They're going to first fill the entire empty orbitals. So over here, the correct answer is 1 2 3 4 and 5, and I hope you get why it's 5, but I don't think anyone would have got 5 just by counting the electrons, because you have to draw these diagrams to make you realize things. Write an equation to represent the first ionization energy of iron. Okay, so you're gonna have an iron in gaseous form, and then what do? You take out one electron out of it, plus one, in gaseous form, plus one electron. Done? Suggest how the value of the first ionization energy of Fe54 compares with the first ionization energy of Fe6. Explain your answer in terms of the factors that affect the ionization energy. So firstly, what they're talking about, they're saying there are two isotopes, Fe54 and Fe56, and they're saying what's going to be the difference in their ionization energy. Ionization energy depends on three factors. Number one is the nuclear charge, okay? Number two factor is the distance of the valence electron from nucleus, and the third factor, which is extremely important, is the shielding. Okay? And all these three factors, they are caused because of either electrons or protons. Nuclear charge because of protons, shielding because of electrons, distance because of the atomic size. Now, iron 56 and iron 54, both of them have the same electrons since they are the same atoms. What's the difference is the neutron number. The neutron number is different, and neutron exactly has nothing to do with ionization energy. Ionization energy has to do with your protons. Ionization energy has to do with your electrons, but ionization energy has nothing to do with your neutrons. And what's different between these two atoms is this one just has two more neutrons. So there's going to be absolutely zero difference between the ionization energy. So how are we going to compose our answer? We're going to say that both isotopes have same ionization energy, because we've just seen that ionization energy does not depend on the neutron number, because they have similar nuclear charge. You're going to tell them that they have similar nuclear charge, which means the same, you're talking about the atomic number, means same atomic number, or you can say the proton number, which is going to be 26 in both cases. And they have this same shielding electrons, and then you're going to tell they have this same number, same atomic size. Okay, so you have to tell over here it was 26 and same atomic size, which means similar distance of the valence shell from the nucleus. Distance, you can say, of the valence shell from nucleus, and that's correct. Why is that so? Because you're talking about two similar atoms, you've just differed the proton numbers. Okay, moving on to the next question, which says that hexene reacts with hydrogen gas to produce hexane. Okay, so you have hexene, you have hydrogen gas, and you're producing hexane. This is catalytic addition of hydrogen into an alkene. Okay, you have a Boltzmann distribution curve, shows the distribution of H2 molecules at temperature T. Okay, sketch on figure 3.1 the shape of the curve with the same sample of H2 molecules when the temperature is increased. What's going to happen when you increase the temperature? The first thing that happens is that your curve moves a little towards the right, and the second thing, the peak drops. Okay, so you need to keep in mind two factors. Firstly, you need to move it towards the right side, and second thing you need to do is lower it. Okay, you need to lower the peak of the curve. So what we're gonna do, make it something like this. We lowered the peak over here, and moved it towards the right. Two things you're doing it, you're lowering it and moving it towards the right, that's all. And for at a lower temperature they asked, or a higher temperature higher, you're gonna do this. And if the temperature is lower, you're gonna increase the peak and move it towards the left and increase the peak. That's the difference. Explain why increasing the temperature increases the rate of reaction 1. Number 1, there are two factors over here. Firstly, more particles have energy. That's a very important point student miss, I don't know why. More particles have energy equal to or greater than I'm going to explain this to you from the equal to or greater than activation energy. And the second factor is going to be that more collisions as particles have more kinetic energy. Look over here. Initially, in front of the activation energy, only this much of particles at the initial temperature, only this much of particles had energy equal to the activation energy. Only this amount of particles were reacting. But when you increase the temperature, what happened? When you increase the temperature, something very unique happened. That now you have added part to it. Now this green part, the particles in this green part, they also have energy equal or more than the activation energy. Initially only the red ones had. Now the red ones and green ones both have. So basically what you've done is you've increased the number of particles. You haven't lowered the activation energy. You've just increased the particles that have energy more. I hope you get it, okay? State the role of nickel when it's added to reaction 1. Simple, it's a catalyst, so it is gonna lowers the EA. Okay, annotate to show the effect of adding nickel. Okay, this EA, this activation energy is gonna move backwards. So that's gonna be your new EA. That's all what happens. When you increase the temperature, the curve moves towards the right. When you add a catalyst, the activation energy moves towards the left. Okay? Define Le Chatelier's principle. Okay, Le Chatelier just said that when whatever you try to do to the equilibrium is going to try to reverse it. So we simply just have to say that Le Chatelier principle states that if we make a change to the equilibrium tries to reverse it or minimize the conditions that are caused to it. Okay, so we just have to realize one thing, that Le Chatelier principle states that if a change is made to a system, the system is going to try to reverse it. If a change is made to a dynamic equilibrium, like if you increase the temperature, it's going to try to decrease it. Dynamic equilibrium, the system minimizes or reverses the change. If you increase the temperature, the system is going to try to decrease it. Whatever you do, the system tries to reverse it. Okay. Over here, reaction 2 shows the equilibrium reaction between X and Y to produce Z in a sealed container. You have X, you have Y, you have Z. Okay, figure 3.3 basically shows the effect of changing the pressure on the percentage yield of Z. Okay, so now over here you can notice one thing, that pressure along this line is increasing. When you increase the pressure, what's happening? The yield is increasing, the graph is going up in both. So you know that when you increase pressure, your Z or Z increases. Secondly, at a lower temperature, there is more yield. Okay, this thing tells you the yield. So temperature lower, Z more yield. Okay, deduce two conclusions. The first conclusion is going to be that whenever we have lower temperature and it increases the yield, what can we state? That we decrease temperature and Z increases. This means the forward reaction is going to be exothermic. Why it's going to be exothermic? Because when we decrease the temperature, the equilibrium tries to reverse it. It tries to increase the temperature. And how will the equilibrium increase the temperature? It's going to increase the temperature by moving the reaction in the forward direction, because forward direction is exothermic. So it will move forward. So what are we going to say? We're going to say forward reaction is exothermic. That is what we can see. Forward reaction is exothermic. And the second statement is going to be from the pressure. Increasing pressure, increase Z. And you know that whenever we increase pressure, equilibrium move towards the side that has less moles. Okay? When, you should know this, when we increase pressure, the equilibrium move towards the side with less moles. So we know that the product side or the right side, has less moles, compared to the reactant side, okay? Or over here they've used these symbols for the moles, A, B and C. So you can tell that A plus B, which is combined, is gonna be greater than C because the reactant side has more moles. Okay? This side has more moles compared to C. That is why increasing the pressure moves it towards this side, because this side has less moles. Okay? Question number 4 we're gonna do in another video. That's it. We're gonna solve question number 4 in the next part.